here is an example of the H and D curve. What this means is that here at low exposure, the film didn't really respond to X-rays very well. It didn't really detect the X-rays. Over here at high exposure, the film became saturated and really didn't respond to extra radiation. So there's just this very narrow range of X-rays from here to here, right? This narrow range of X-rays that could actually produce the image. So when using film, you as a technologist had to be very, very accurate with your technique. You couldn't just go with whatever was on the console, just press the button and expect the image to look good, right? No, you had to look at your patient, you had to estimate about how thick they were, you had to go to your technique chart, take a look to see what to set your KVP at, what to set your mass at for that size of a patient, and for that kind of anatomy. And then you would hopefully get something that was in range. If it wasn't, right, it would either look too white or too dark, and there was no such thing as windowing or leveling because it was on film, right? It was a physical piece of film. You couldn't change it. So that was the good old days. Nowadays, we have digital image receptors. Rather than the H and D curve, these display a linear response. Right? So these blue dots are a linear response, right? Straight line. That means, right, at this latitude, you can actually have a much lower exposure. Right? At this latitude, you can have a much higher exposure, and you would still be able to get a good image. So the types of exposures you could use, right? The range of techniques you could use expanded, right? Things that would have been out of range previously were now acceptable. It could still give you an okay image, where before it would have been either overexposed or underexposed. So dynamic range is the range of exposures or intensities that can be detected by the IR, right? If you shoot radiation at your receptor, will the receptor actually be able to notice that there's radiation, right? Film screen has a very narrow dynamic range, so it only notices radiation in a small area, right? Either it's too low, it doesn't notice it, or too high, it doesn't notice it, right? Digital has a wide dynamic range. Even a little bit of radiation can be detected by digital receptors. Okay. So as far as DR goes, we typically have a dynamic range between 0.1 microgray to 1,000 microgray.
What gray, sir?
Microgray.
Micro.
Now, there is another term called exposure latitude. A lot of people use dynamic range and exposure latitude interchangeably. But there are differences between the two, if you get really technical about it. Exposure latitude is how much you can be overexposed or underexposed and still get a good image. Right? So, for example, this is the entire range that I can detect. Exposure latitude is saying that if my image only shows this exposure here, I have the ability to shift along this detection range and still get a good image. Okay?
Wait.
So hopefully the next diagram will
Okay.
let this make a bit more sense.
Wait, I didn't get that.
And you do have this PowerPoint. I believe this was sent out to you last week. That's good. It's still good too. These are the possible X-ray exposures that could happen. Right down here, really, really low, underexposures. Up here, really, really high, right, overexposures. With digital, we said that the dynamic range is here between 0.1 to 1,000. So as long as when I shoot, the exposures on my image fall somewhere in this range, I will be able to see it properly on the IR. Now, if the exposures are too low, that is underexposure. I get that quantum model, right? If it's over here too high, I have saturation and I have too much dose to the patient, right? So the dynamic range, the range at which we can detect X-rays, should belong somewhere here within this dynamic range. Does that make sense? So our goal is for all the X-rays in our image to fall somewhere in here. So for example, this here could be our optimal exposure, like somewhere here between 1 to 100 micrograys. But if my technique was too low, I could have it all the way down here. And it's still going to be acceptable, right? Because it's inside my dynamic range. If my technique was a little bit too high, and I shifted this across this way, so it ended up over here, that's still okay. It's within my dynamic range. So my image wouldn't look any worse, any better, or any worse. Right? Yes?
So exposure latitude is within dynamic range, but not in the optimal area?
Correct. So exposure latitude would be, if this is my optimal, how much can I move my optimal and still get something that's okay? Right? So that's exposure latitude. Latitude is just like how much freedom you have, right? How much freedom do I have to change my technique and still get something that looks good?
Minimum and maximum.
Like minimum and maximum.
That makes more sense.
So I could have this here, here, right? Anywhere inside my dynamic range, the picture would look normal. It might be a little better or a little worse because it's not optimum. Right? So it might be a little worse either way since it's not optimum, but at least it will be an acceptable image. Okay. Now, if for example my optimal exposure needed more dosage, right? So let's say that let's do doing something else, right? So my image needed X-rays from here to here to create a good image, then my exposure latitude has shrunk, right? I'm using up more of the dynamic range for my image. I don't have as much freedom to move back and forth anymore. Okay. So dynamic range and exposure latitude are both kind of similar in that they talk about how your exposures are able to change and you can still get a good image. Right? They're both kind of talking about that. But dynamic range specifically is just, this is what we can detect. Exposure latitude is, this is how much we can move back and forth within that dynamic range and still get something good.
So what's the difference between this picture and that was right before?
So in this case, I'm using a wider range of doses to create my image. So my exposure latitude isn't going to be as wide. So just pay attention to the yellow line up here. Notice that it's bigger on this one right, compared to this one. I don't have as much wiggle room on this one.
We're talking about the exposure latitude, the wiggle room, you said?
That's right, your exposure latitude is your wiggle room, basically. Now, if you have a poor exposure, right? If you do use a poor technique, right? A KVP or a mask that's not correct, then what you end up with is something like this. Right? Part of your image is inside the dynamic range, part of your image is outside the dynamic range. So in that case, this part of the image isn't going to show up properly. Right? So in this case, this is the lower end. So your whites, right, aren't going to show up properly. Right? Your low dose areas aren't going to show up properly.
What's that called?
Okay. So this would just be underexposed. It's no longer an acceptable image, it's underexposed. It's too far in this direction. Right? If it's the opposite way, it would be overexposed, right? Too much radiation. And remember, with film screen, right, you didn't have as much wiggle room as you do here. So The good thing about digital is that you do have a lot more freedom, a lot more flexibility. If you use the wrong technique, you don't need to repeat your image. It gives you the ability to adjust more easily. It's a good question, I suppose. Partly to understand the concepts of over and underexposure, and partly to appreciate how far we've come since film screen. Okay. So now let's talk about pre-processing and post-processing. So what does the prefix pre mean? Before. And how about post? After. Great. So we're talking about before and after something. What do you think that something is?
The image.
Before the image, after the image. Specifically, which image?
X-ray image.
Manifest image, yes. So pre-processing occurs before the manifest image, before it pops up on the screen. Post-processing occurs after the manifest, after it pops up on the screen. Okay. So because we do have a wide dynamic range, we do have exposure latitude, we are able to do things like leveling and windowing. We have that ability. Okay. You can create images even if that exposure is outside the optimal range. Okay. If you leave the images as is, they will not look correct. So, if you shoot an X-ray and you do not have pre-processing, your image will actually look really strange. It's because we can kind of make use of some of that dynamic range and exposure latitude that we can adjust our image using the histogram in order to make it look nice. Okay. So, like we said earlier, pre-processing occurs before the image appears on the screen. Post-processing occurs afterwards. So pre-processing is not something that you would do. Right? You do not manually pre-process an image because there's nothing for you to mess with. Everything that you would do would be considered post-processing. So anything that you see your text do to adjust your image would be called post-processing. Pre-processing all happens before it ever pops up. So, here are some things we're going to talk about in regards to pre-processing. Okay. So, we talked about this before, right? Quantization. That was the previous section. We're going to be talking about the histogram a little bit more. And we're going to be talking about corrections. Things that are done to the image to fix it before it shows up. So automatic rescaling, flat field correction, and dead pixel correction are all things we are going to be discussing. And so we will start with automatic rescaling. Okay. So automatic, what does automatic mean?
Without any effort.
Yeah, it does it by itself. Requires no intervention, right? Requires no input. Okay, scaling. What is a scale?
No weight.
So, right, you think about weights, right? We also have something called a grayscale, right? What is the grayscale? Right, number of grays, number of colors, right? Related to bit depth, right? Talking about our contrast, right? How many colors are we working with? That's our grayscale. What does the prefix mean?
Again.
Again. That's right. So we do it again. We repeat, right? Redo. So we are going to redo the grayscale automatically. Why do we need to redo the grayscale? In order to hit a target brightness and contrast. Okay. So the image that we start with. Okay. Think about your CR processing. When you're at the clinics and you run the CR cassette, and you know how sometimes the tech checks the image as it pops up on the screen? How does that image look as it comes up on the screen?
Super white and gray.
It looks kind of white and gray, right? It doesn't look nice like your normal image, right? Only after the whole thing pops up does it take a second and then suddenly, bam, it looks nice, right? So that initial image is actually what is being collected. That's your raw data. Afterwards, you take that raw data and it rescales into the proper image. Okay? So your CR readers actually give you kind of like a behind-the-scenes look at what's happening in the pre-processing. Right? Your true manifest image hasn't come out yet, but it's giving you a sneak peek at that image. And so that is what's right before automatic rescaling occurs. That image you see.
Mr. Phung,
Yes.
quick question. Okay, so you said the before image, like before it pops up, that's what is being collected is the raw data, and we take this and do what with it?
And then we will end up converting it into the final image.
Okay.
So this is your true manifest image, right? This is the image that we're actually going to see.
Thank you.
So it's like a preview of the manifest.
Like a preview of the manifest.
So in between these two images, you're doing the post-processing, sir?
No, this is pre-processing,
This is pre-processing.
right? You're not doing anything to it. The computer does it automatically. So, how do we do automatic, or how does the computer do automatic rescaling? It does it through something called a lookup table, LUT. Make sure you do know this vocabulary word because the registry loves to throw this in there. Okay. So, we use the lookup table to change our raw data into that final image. So what's going on? Over here, we have our grayscale for the raw data, and we have a histogram here. The lookup table, right, is its own histogram. And so the lookup table says, well, if you've got a value in histogram A, we're going to convert that value into something else in histogram B. Right? So it's going to be like, all right, you've got this value here. I'm going to take this color and change it to this. Oh, you've got this color here. I'm going to take this color and change it to that. So it's going to expand the size of that grayscale, right? It's going to take something like this narrow and expand it here across a much bigger range of colors. So that way you have more blacks, you have more whites, you get more contrast, right? You're not just stuck in this narrow range of grays. Now you have black all the way down to white. Okay. So the lookup table is just, all right, pixel value here should become a different pixel value. Pixel value there should become this different pixel value. So it looks at the brightnesses of the raw data and changes those values to match the lookup table, right? The reference histogram here in the lookup table. Okay, and of course, right, this is per anatomy. This is by anatomy. So it is important that it is processed under the correct anatomy. Yes?
So you're basically saying that when we click a upper extremity on the like when we're dealing with CR in the clinics, when we click up upper extremity, whatever, that's kind of what you're saying. It's setting it up to the, expecting that on the image.
Correct. So when it's coming up, right, it's getting the raw data, and then it uses the lookup table to be like, all right, for this kind of anatomy, for a chest, if the raw data is this kind of lightish gray, we're actually going to make it white. If it's this kind of darkish gray, we're going to make it black, and then the stuff in between will sort of spread out here as well. Right? So rather than just a very narrow range of colors, right, only a small range of colors, now you get the full range of colors. It's taking that thing and spreading it out. Yes?
So does this happen like basically right there before we get our image? Like right before we get our
Right, so in CR, right, I told you that it gives you that sneak preview, right? In your other machines, right, you don't ever see this, right? It just pops up looking nice,
Okay.
right? But the idea is that the machine collects the raw data from the ADC, right? The ADC's got that raw data. The raw data makes that histogram, and then from that histogram, it just goes match, 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 fix, 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 and then what pops up is your final image.
And this is all within the lookup table?
So this is all dealing with the lookup table. And so the lookup table just takes your original numbers and adjusts them to be your final numbers in the new histogram. Bless you.
Thank you. Sorry, I didn't mean to
No,
scare
no,
you.
not you. I'm just seeing all this information. That's why, not because of his needs.
So do you kind of see how this lookup table works, right? You see how if you have a color here, it just matches it to the graph here, and then that's how it calculates its new value.
Mm.
So does it just flip it? It just looks like it kind of.
So it's not flipping it, right? Because light colors are still light,
Oh, okay.
dark colors are still dark. It's just spreading it out.
Okay.
Mhm.
You said it matches it takes this color and matches it.
Right, so these colors have numbers, right?
Okay.
That's what quantization is, right?
Uh-huh.
We're assigning numbers to the colors. So like, all right, this color has a number. I'm gonna run it through this lookup table, this graph here, and, right, so it hits the graph, I come across, and it's like, all right, now it has a new number now. And that new number represents a new color. So here you see it's kind of closer towards the middle, closer to 1024. Here it's really far away now, like it's closer to 500.
Okay.
And if you look at the color here is a bit darker, the color here is a bit lighter, right? Because the lower the number is, the lighter the color is.
It's expanding the grayscale,
Expanding the grayscale,
provide more colors to the image.
correct. Any questions here so far? Just remember, the raw data only has a narrow range of colors, and our end goal is to expand those colors so that we have an image with white and black, not just gray. Right. So, okay, another diagram of how the lookup table kind of works. Right, so you start off with this image here. This is our raw data, right? You see that the colors have numbers, right? That's quantization. You take those numbers, run it through the lookup table. Lookup table is like, all right, anytime I see a 40 here, I'm going to switch that to a 90. Anytime I see a 30 here, I'm going to switch that to a 10, right? And so at the end, those numbers get converted, and you can see that we are using a much wider range of colors now, right? Instead of just dark gray and light gray, we actually have black and white now.
Does this work by a fixed ratio? So that like, okay.
So the fixed ratio is that lookup table, that histogram.
Oh, right.
So this curve right here, right? So once again, just like the previous one, right? You've got this color here, bounce it over, right? So you see how these are really spaced close together. By the time we get our final image, these values are spaced farther apart. So we have a wider range of colors. So raw data down here, final data on the side. Right? That is our processed image. Okay. All right, so any questions about the lookup table or automatic rescaling? Are we okay with this concept? And when does this take place?
Pre-processing.
Pre-processing, right? Before the final image pops up. CR cheats, it shows you that preview, right? So we don't count the preview, right? It's before the actual final image pops up.
So that's why in CR it always looks like a lot more gray.
Okay, correct. All right, next up, we have flat field correction. This one is really interesting. So, if I have an IR like this, right, and I have nothing in between the IR and the tube, right, and I just shoot an X-ray with nothing in between the IR and the tube, what do you think will show up on the computer
A
as our
blank
final
image.
image?
A blank screen, just dark.
Nothing.
It
just
should look
black.
blank, right? It should just look dark, right? X-ray should have just covered the whole thing. Should it look evenly dark the whole way through?
It should.
Should be, but it don't.
It should, but it doesn't, right? So you would expect the same number of X-rays hit the whole thing, so the whole thing should be the same density, the same color. But that doesn't necessarily always happen, right? Depending on the detector or the tube or variances in how the detector or the phosphor or the scintillator is performing, it may look different in different areas, right? One corner might be slightly brighter, one corner might be slightly darker. And we don't want that, because those areas of brightness or darkness could also show up on an X-ray that has anatomy. And at that point, it could change the image to look like pathology, right? Like, imagine you had a detector that had a white that was lighter in the middle than the edges, right? It was more white in the middle than the edges. And then you shoot a chest X-ray. And so the lungs, which are in the middle of the IR, now look whiter than normal. That could potentially look like pathology, right? It's like, oh no, there's consolidation in the lungs. There's some sort of density in the lungs, right? So we don't want that to happen. We want the whole thing to look even the entire way through. So that's what flat field correction is about, right? Because if you think about it, right, some densities are higher, some are lower. It's not flat, right? We're trying to even it out so that everything is the same color, the same density by default. And the only changes in density should come from the anatomy, not from whatever's going on inside the receptor. Does that make sense? Okay. So, what happens is that we do flat field correction through calibration. We take the IR, we shoot X-rays at it, and then the IR detects those X-rays, and then the IR thinks to itself, all right, this is in calibration mode, I got the X-rays, I know there's nothing in between me and the tube, everything should look the same. So it checks its values, right? Goes through the histogram, looks at the values. All right, here it's nice, here it's nice, here it's nice. But then some places it notices are a bit brighter. Some places it notices is a bit darker. So then it memorizes those locations, and it thinks to itself, well, next time I get an X-ray, I'm gonna automatically take this brighter part and make it look a bit darker. I'm gonna automatically take this darker part and make it look a bit brighter, so that it looks even. Does that make sense? So it memorizes the parts that are off, and it adjusts the brightnesses so that it looks correct. And so afterwards, when you shoot a patient, that sort of correction, a flat field correction, will be in effect. So it will automatically adjust it for you. So that way your image looks correct, looks proper. So any changes from the correct brightness are measured during calibration, and then it accounts for those differences in the following exposures. So any questions about this one, flat field correction? Yes?
You said it remembers the parts that's off and adjusts the brightness, or what is it? Or the anatomy? What is it adjust?
Right, so it adjusts the brightness, it adjusts those pixel values. Right, so if everything's supposed to be 50, And over here in the corner, it notices that the values are 40 instead. When you shoot the X-rays, nothing in between, it just automatically ends up 40. It's like, oh, that's not right. This should be 50. I'm just gonna add plus 10 to these values next time. So you try it again, everything's 50 except this area, right? Well, since it added plus 10 on top of the 40, it also looks 50, right? So just automatically corrects for it. And then when you throw anatomy on top of it, doesn't matter, it still automatically makes that adjustment.
Is it just because like the machinery gets old that it does that, or it just comes naturally like that?
It's just natural, right? Because you've got the different detectors, right? Either they're your TFTs, right, or your CCDs or your CMOS. Like they're not all exactly identical, like they all have slight variations. So we just need to calibrate them, put everything onto the same level. We're basically just setting a baseline for all the detectors inside the IR. All right, any questions? Any other questions? So far, so good? Guys are tired. Rough weekend?
A lot of people do that. A lot of people do.
I hope that's better next time. All right, let's talk about our next type of pre-processing, which is dead pixel correction.
Like we're feeling right now. Dead.
Feeling right now? All right.
Dead.
All right, let's take we can take a 10-minute break.
Yeah.
But first, before we take our 10-minute break, dead pixel correction. What on earth is a dead pixel?
Dead one. Just
What is
You
that?
can't.
Doesn't it detect exposure, Shamika?
I was gonna say that. It's dead.
just
Yeah, okay.
I'm gonna say
Right, so it's dead, it's non-functioning, it can't do its job.
Yeah.
Right, like when you guys finish taking Miss Ponia's exam and then you come into my class afterwards, you guys are dead, right? You're not even functioning.
We are definitely dead.
Right? So I'm trying to send information your way, right? But no information is being detected.
Right.
Right? I'm trying to send X-rays at these dead pixels, but no information is being detected.
That is such a good analogy.
So, occasionally, we do have pixels inside our TFT arrays or like our CCDs that just are no longer working. Right? For whatever reason, they have failed. Right? I mean, it's electronics, it's computers, you expect things to occasionally fail. So, what do? If you don't fix these pixels, what's going to happen is you will have a pixel that acts like it received no X-rays. And so, when it comes time to create the image, you will have this point somewhere on the image that is just pure white, because it received no X-rays. Make sense?
Yes.
Right? So you don't want like random white dots in your image, because once again, it can mimic pathology. So we need a way to get rid of these white dots, or at least hide these white dots, hide these dead pixels. And so we do this through calibration and then correction. We do calibration to find the dead pixels. And then the computer gets to work. It looks at that dead pixel and it says, all right, well, this pixel is dead, but what do I know about this pixel? I know that this pixel is next to some other pixels, right? It has some neighbors. And anatomy doesn't change drastically within one pixel, right?
Right.
Normally, if you have two
Very
pixels next to each
fine.
other, they should be kind of similar, right? So what I can do is I can look at all of the neighbors, look at the colors of the neighbors, and sort of
Pause.
average, right, estimate a color for the dead pixel. And then even though the dead pixel is not giving me a signal, I'll just pretend that my estimate color is the color of the pixel. Does that make sense? Right? So, for example, I've got a picture here, right? Martini glass. There is a dead pixel somewhere in here.
Where?
That's my question.
The olive.
Which of these pixels was the dead pixel?
That's
Olive?
super dark.
The super dark spot.
Right there?
Here?
Yeah.
This one pixel here?
Well, now.
No.
6.
No, there's one dead pixel somewhere.
Okay, hold on.
There's a single dead pixel.
Higher. Keep going, keep going, keep going. Keep going, keep going. Come on. A little more. One more. To the right. Keep going. You know the drill. Might as well take a bigger step. Right there.
This pixel here. You think that was the dead pixel? I think so.
No.
Isn't there supposed to be an olive there?
I think the spatial resolution is so poor you can't see the olive properly.
Mm.
Where is the dead pixel? So it doesn't look like there's a dead pixel here, right? Everything looks correct.
Oh.
But in reality,
Yeah.
this is what happened.
You were close, Jay. You said you told him to start.
There was a dead pixel right here.
You were?
Yeah.
But
you were
all I
close.
did was I averaged the colors of these 4 pixels surrounding it, found the average color, and gave it that average color.
How do you know that's the dead pixel?
So
There's 3 corners in that same like section that are all like a lot darker than that one.
So normally you wouldn't be able to tell just looking at the image. And that's exactly the point. You're not supposed to know where the dead pixel is by looking at an image. It's supposed to correct it to the point where it looks normal. Okay? So rather than having dead pixels inside your image, we just hid it by giving it the average color of the surrounding pixels.
What would a dead pixel actually look like? Does no one know?
So a dead pixel would look white, would be pure white. Because a dead pixel means it isn't collecting X-rays. And if there are no X-rays, it looks white.
All right.
So dead pixel correction.
Pick my food.
Once again, this is pre-processing, right? This all happens behind the scenes before that image ever pops up. We do. We do have the lady coming in at 1:30. That's right. So fortunately, we've hit a pretty good stopping point. So we were able to get through all of our pre-processing techniques, right? We got through automatic rescaling, we got through flat field correction, we also got through our depth pixel correction. And then we had a chance to talk about dynamic range and exposure latitude. So any questions about what we've talked about? Yes, Jay?
That line, overexposure, underexposure, latitude, all that good stuff. We need to know that, like, because there are 3 different charts or whatever.
So for
and I couldn't really tell the difference between the.
So the key things that you should know about exposure latitude and dynamic range are their definitions. Right, so make sure you do know their definitions. The definitions can be asked in different ways. Right, so just be able to understand the idea behind it. Right, don't look for the definition word for word, right, but be able to be flexible and still understand the definition in various contexts.
I guess I should have worded it more so like, the images you have show page, or 4, 5, and 6 show that dynamic range doesn't change, but the acceptable exposures do, and I wanted to know why that was.
So in that case, we are just assuming that our dynamic range is staying constant, but the range of exposures, the range of doses that we need to create our X-rays are changing. So
those
maybe
are just
you have,
different examples.
so like, let's say that you've got an anatomy like,
Hand.
okay, so let's say that you've got anatomy like hand. So for hand, right, perhaps it's really easy to overexpose, really easy to underexpose, right? Because it's so thin that if you change things a little bit, you'll see big changes in the image. In that case, you have something that's more like this, right? In that case, you don't have a lot of wiggle room. So the optimal exposure, right, covers this range of exposures. You only have a little bit of room to move around. Otherwise, you end up overexposing or underexposing.
So that's for thinner anatomy. That would be more like the 4th page that you have.
So I don't want to say that it's exactly for thinner anatomy because there's other things going on there, right? So, for example, no, you know what? That's fine. That's fine. You can think of page 5 as thinner anatomy, page 4 is thicker anatomy.
So okay. But we shouldn't expect to see graphs like these and then the text. Okay.
Now, I'm not going to ask you about graphs like this. These are just to illustrate the concept of exposure latitude versus dynamic range. Yes.
So the depth picture, will there ever, like, are they always gonna be together? Or it's only like one depth pixel?
Great question.
Or like, is it scattered or?
So, ideally, it's only going to be just one depth pixel or they're going to be scattered. But sometimes we end up with like a whole row of depth pixels or a whole section of depth pixels. And if that happens, suddenly depth pixel correction doesn't work as well. Right? If you've got a whole group of depth pixels here, right, you can estimate the colors for the edges, but how are you supposed to estimate the center of those depth pixels? Because there's nothing around for you to estimate off of. So yes, in those sort of situations, depth pixel correction would fail. And so in those sorts of situations, you would just need to flat out replace the IR.
Are there cases of missed pathology because of dead pixels?
Not that I know of. Although that might be an interesting research topic.
Like just how often techs are properly calibrating things and checking?
Well, I mean, just sort of like the pre-processing techniques, new pre-processing techniques and their effects on pathology, I suppose.
Essay topic, there you go.
Although I don't know how much research there actually is on something like that. Let me see if
Good thing that she can duck her own.
she's on her list.
Just punch a detector a couple times and wait.
Alright. She doesn't show up soon, but she's just gonna start with post-processing.
Jay, how's your essay going?
I've started brainstorming.
All right, good, good.
No.
Hey, man, it's a start.
Now,
I like your
post-processing
topic.
isn't actually that bad, right? If you look at it, a lot of
I
this
got like
stuff
4.
is
I'm trying to figure out which one
relatively basic.
actually.
Right, for example, leveling. We've talked about leveling before, right?
Yes.
Window width, contrast. We've talked about windowing before, right?
Yes.
Electronic cropping, masking. You've seen this in clinic before, right?
Yes.
Right, okay, stitching. That might be kind of new to some of you. Although,
Scoliosis.
right, if you've done scoliosis, like at Bentall Bone Clinic, you may have seen stitching in, at work. Edge enhancement, okay, this is probably pretty new unless your OR type was fancy and showed you this on the OR machines. Equalization, probably haven't
you
seen
talking
it.
about the, when they, is it shrinking or, turning it? I can't
No.
remember. Which one is that on the?
That would be this one here, image flip.
Yeah.
Have you seen your text rotate images, flip them back and forth, right, to make it look the correct direction? Right? You know about image
And then
flip,
you flip it and try to
Annotation.
put PA on it or A, you know, like when you-
perhaps. Right, annotation.
Mm-hmm.
You've seen text do annotation even when they're not supposed to,
Mm-hmm.
right? Image inversion. We haven't really talked about this, but it's not very difficult. You're just flipping colors. And then magnification, right? Being able to zoom in or zoom out on an image. You've seen this before as well, right? So really, post-processing isn't that difficult. A lot of this is either stuff you've seen in clinic or is kind of common sense. It makes sense what it is. Okay. Right, so we'll go ahead and keep talking for now. Windowing. What did we say? Windowing changes.
Brightness.
Brightness.
That's leveling.
Oh, contrast.
Contrast. Great.
Right.
So window width, windowing, contrast, leveling, window level, brightness.
Those dang residents.
Yeah, those same residents, right? Okay. So, right, windowing, right, changing the contrast. We've got a narrow range of colors. you just expand your range of colors or narrow your range of colors. Now, here's something. Oh, okay, looks like the lady will be coming in on Wednesday instead.
What?
Okay.
Text her back and tell her.
And that's pretty tardy.
That's
After we did that, all our stuff.
Yes, a 2-day target.
Perfect light must have been.
So, something to keep in mind, and this is a topic we'll also get into later. Just because the image itself says it has a certain window level or window width, doesn't necessarily mean you can see it on the computer screen, right? So the image itself may say, all right, you've got this much window width and this much window level, but you need to be able to see those changes on a computer screen. So the computer monitor needs to have enough luminescence. Luminescence is brightness in order to display all the shades of gray. And so there are actually standards as to how bright a radiologist's monitor should be. Okay, and we will talk about that later on. So look forward to that. All right. Oh, all right. So I didn't have this on the initial list, but region of interest. This one is not something we really do a lot with. Basically, we can kind of grab an area and ask, okay, what is the brightness of the pixel here? Right? We can get the value of the pixel or of the area. That way, we can kind of figure out if it is brighter or darker than we expect it to be. Okay, but we don't do a lot of this in normal radiography. Right now, if it's something like dental, right, you can do this to be like, all right, is there any sort of like bone disease here, right? How are like the gums, or how's the bone there doing? Right? Does it look as dense as it should be? Does it look less dense than normal? Right? You can use it to check things like that. All right, electronic cropping, otherwise known as masking. This is reducing the field of view, right? Reducing the amount of anatomy you can see. But because it's post-processing, this happens after the exposure, right? So some people call this post-exposure collimation. It's like you're collimating, but after the X-rays, not before the X-rays. What's the problem with collimating after the X-rays rather than before the X-rays?
You're not really doing anything to help the patient.
It's still got the exposure.
Okay, so you've still got the exposure, you've still got the patient dose. So you're really not doing anything to help the patient, right? If you're doing a hand and you open up your light 17 by 17 and you blast the entire forearm, and then afterward you're like, no, I'll just crop it to this nice little hand right here. I mean, it looks nice, but the patient's arm still got blasted by X-rays, right? So what is the point? So cropping, masking, right? Not a substitute for collimation, right? It does not reduce patient dose. What other issue comes with ignoring collimation? Scatter, right? X-rays hit a wider area. There's more stuff for it to scatter off of. And then when it scatters, the IR picks it up, and now your image has more scatter on it. It has more fog on it. So your image quality looks worse because of poor collimation. So actual physical collimation is still very, very important. So if we're supposed to be physically collimating, why would we ever need to use cropping or masking?
Because you've done mistakes.
Very good. So in the case the computer cannot detect the collimation, in the case of a histogram analysis error, where it gives you all the data, then yes, you can go ahead and crop the correct portion out. Okay. But this should not be something that is going on constantly, right? This is not something you should make a habit of doing. Yes,
Mr.
Shakti.
Phung, I have a question. When you crop, when a technologist crops an image, then the radiographer, no radiologist, tell that it's been cropped?
Yes. Yes, it is. Well,
If
it
you
depends.
didn't,
Careful
It
how you say
depends.
this.
But in a lot of cases, yes, it is possible to tell it's been cropped. How? Because on a manually collimated image, normally when you look at the edges, you will see a little bit of white fuzz on the edges of your image, right? And that's just because, right, the computer can't perfectly find the collimation, so it chooses what it thinks is the collimation. And of course, your collimator isn't perfect. It's not going to be perfectly black to white. There's going to be a little bit of fuzziness in between. And so you'll see that fuzziness. So let's see if I can find an example of what I'm talking about. Let's see how many people have actually collimated properly. Where do we want to go for a good collimation?
You want to look at my
I'm going to try and throw the Bentall people under the bus.
look at my fingers.
Let's see how to
Keanu.
Let's see how to explain the Bentall people do it.
They like leaving it open too. It'll get on you if you close it.
Ooh, that did not look great.
Hmm.
That looks like toast. Looks like, what's that, Nancy?
Last week I worked with a tech, she was doing the third digit.
Same guy.
And she had the collimation all the way open to here,
Mhm.
but she thought she had to get this joint too. And I was like, you're doing your finger.
Or a finger?
It's just
Who's
the
king?
MCD.
Mm.
And she had it open all the way to here. And then like I didn't say anything. I was thinking like that's too much. And then but she didn't do anything about it. And then later on, like I was looking in my pocketbook, and then she's like, "Oh, let me see." And I was like, "This is you mean you just did a hand basically?"
No.
I was like, "Why would you need this joint? You just do your finger."
Well,
Ooh, that's a mean
luckily they
fracture.
had enough, I guess.
You see it?
What's the word I'm looking for?
Look at that fracture.
Did enough self-reflection to ask you afterwards and to check afterwards. So hopefully they know that.
She's kind of new there. But
Yeah, that makes sense.
Who, Amy?
T.
Okay, so. Alright, so over here, right? You see this area of white fuzz? Right? That's what I expect to see on a
Post
properly collimated image. Right?
Not
If
post collimation.
if it's post, then
First digit?
I will most likely not see any fuzz at all. Right? Because normally when people collimate in post, they collimate smaller,
Base.
which means that you will not see this fuzz.
I see a line on the base.
Look at the side.
So that's,
Mr.
this
Phung,
is a
where's your?
proper collimated image.
So
They mask.
I didn't say it's proper collimated, I just said that it's not post collimated.
On this
I
side.
don't think it's post collimated because I can see the fuzz.
Okay.
On that side, because the other
And
side's
that
over
on
first.
one side of the image, you'll always see like this several times. On a
Ideally, you'd see it on all four sides.
Sometimes I see them crop out just like the white parts, just because they want to see the Instagram. Because I asked one time,
Mhm.
and they said they don't want to send it to the radiologist like that.
Mm.
Because they're sitting
Oh,
in
the dark room?
dark room.
Mhm.
Alright, that's fair.
That's their protocol.
I mean, as long as it's not a significant change,
As long as like the bones are already white though, so like
that's true as well.
Yeah. But I don't argue that. Okay.
In that case, I mean, just personal preference at that point. Personally, I don't like to crop in post, so I just leave it as is. I leave the white border. So that's kind of my proof, my demonstration that this is my actual collimation. Yes, Jones?
Can they also trace back to all the post collimation you've done? Or post
Like they can
processing
revert
you've
it,
done?
right?
They cannot
That's what she
revert it. Thank you for bringing that up. So we're going to talk about this at the end of all
So you
these
like-
post-processing techniques. But when you do post-processing, you have to be very, very careful with what you do, because some of these are irreversible, and you will cause a permanent loss of information if you do them. For example, windowing and leveling. You shoot a picture, it's got a certain window level, it's got a certain window width. You change it before sending it to the radiologist. Guess what? The image saved in the system is the new data that you changed it to. The old information is permanently gone. It has been lost forever. And it's possible that, right, you have decreased the quality of the image, and now they can't ever put it back to the way it originally was. So you need to be very, very careful with what you do in terms of post-processing. Okay, I think Jay had something first.
I didn't raise my hand.
Yeah? Okay,
So
Shahid.
what do you mean decrease the quality?
Okay.
Because when you're just cutting out the side, how are you decreasing the quality?
So my example was talking about windowing and leveling, changing contrast and brightness.
So the original contrast and the
Right, so for example, and we're going to talk about this later as well. You are at your computer screen inside the X-ray room. The image pops up on your computer screen, you look at it and you say, you know, this image looks a little bit bright. Let me change this. Let me darken the image, and let me also increase the contrast so the bones show up better. Right? And then you send it exactly like that with your changes, with your post-processing. When that image gets to the radiologist's monitor, they have a completely different type of computer monitor with completely different standards. So the way the image looks on your screen is not how it looks on their screen. You changed it so it looks good on your screen, but now it may make it look bad on their screen. And they no longer have the option of getting back to old information because you post-processed. So rather than trying to make the image look good for the radiologist, send it as is and let the radiologist make it look good for themselves. Does that make sense? It doesn't matter what it looks like on your screen unless it's obviously bad, in which case you might be better off just reshooting it, right? But just send it across to the radiologist, let them handle the post-processing so that they can make it look good on their own screens.
Does their computer have its own form of rescaling then?
So it's not that it has its own form of rescaling, it's just that due to the standards those monitors have to meet, images will look different.
And is that only pertaining to windowing and leveling, or is it like any post-processing?
So any post-processing can cause loss of data.
So if you do something, okay, so if you mess up and then in the post-processing you fix it, that evidence of the mess up is gone if you send it like that?
Correct. So for example, if you use the left marker on a right hand, and you're like, oh no, I mismarked my patient, but I don't want to reshoot this x-ray. Let me be sneaky, crop out the marker, and then put an electronic marker on here with the correct side. Will they be able to pull up the old information? No, they won't. So, yes, you have successfully hidden your mistakes. Should you do that? No.
So better than
Digital markers for everyone.
Is that ethical, right? Is that something that you should be doing? No, you shouldn't do that.
What is ethics? Seriously?
But
Is it done?
is it done?
Yes.
It is done.
Did they live?
Sir, I had put the wrong marker, and then my technologist fixed it, and that was a better thing to do than to put it to expose the patient again. Right, sir?
What argument she?
It
So
was-
that is a
No, it was like I mean, it said more.
You say
Right,
right.
right, sir.
that is an ethical question, or more question that we can talk about at a later time. Right now, I'm just gonna say straight out that you should not be doing that.
You saved life.
should. But trade-offs, right? Exposing the patient again versus changing it, right? That's a different discussion that we'll have to have at a different time.
Honestly, your tech is a hero. They didn't re-expose that patient. You saved their life. You're doing good.
Next one, stitching. This one is really straightforward. What does stitching mean?
Attaching by attaching.
Bringing it together, right? Tying it together, right? Stitching it together. All you're doing is taking two separate images and combining them into one. Or sometimes three images and combining them into one. Right? That's all it is. If you don't stitch them properly together, however, right, the computer can't figure out where the overlap is, then you can end up with an artifact. Okay, but normally, it should be okay.
Normally it's just 2 images.
2 to 3, depends on your machine. Okay, next up, edge enhancement.
No.
So, enhancement, what does that mean?
Make it better.
Make it better,
Enhance.
right? Make it more clear, right?
Yeah.
Enhance, right? On the climb shows, right? Zoom in, enhance, right?
Reveal.
Make it more clear. Okay, edge. What kind of edge do you think we're talking about?
That was kind of weird.
Edge of the anatomy.
Oh.
We are making the edge of the anatomy more clear. So if you look at these pictures going from left to right, do you notice how the right side seems to pop a little bit more compared to the left side? Right? The edges are sharper, they're a little bit more clear. Right? That is edge enhancement.
So
I can show you that here as well.
There you go, Mr. Phung.
Go ahead, Nick.
I was gonna ask whether or not that is something that we should be doing for everything, like.
No, absolutely. Not unless your doctor requests it.
No, I'm trying to. So like, if it improves image quality, then why isn't it done like automatically as a part of pre-processing? Is what I meant to say.
Because that's not something you're always going to be looking for.
Okay.
So, chest X-ray, right? I'm going to take this and I'm going to sharpen the image. This is edge
No,
enhancement
they
right
angled
here.
it. Yeah, look at the clavicle.
You see how that suddenly pops? You see that how the edges of the bone suddenly become a lot more clear?
It's angled for sure.
Right. It does look a little bit ugly.
Yeah, it does.
But for lungs X-ray, this is not a good image.
Right?
I don't know
But
why
as
they
you can
would
see,
angle,
right?
but it looks like it's.
So it's basically making the image clear? Is that what this edge?
It's a different angle.
So it makes the edges of anatomy look more clear. Sometimes you don't necessarily always want the edges of your anatomy to be clear. Right? Sometimes you want to be able to see the fuzz. Right? But if you're like trying to figure out, okay, where's this bone supposed to be? I can't quite see the bone, right? Sharpen it up. Right? Like for example, from here, something like the SC joint, right? You can kind of see it here. Right? You can kind of see the sternum, the manubrium right here, right? But you take this and you sharpen it up. It shows up a little bit more clearly now, right?
So that's sharp low.
So yes, this is low edge enhancement, medium edge enhancement, high edge enhancement.
Yeah,
They do have a mask on, like I noticed that, right? Super high edge enhancement.
So this needs to be collimated more, right?
Get it, Shane.
This could be collimated more, yes.
On the side.
They have
Side
like
views.
asthenic.
That's right. Aesthetic.
It's not angled, it's not
Could the tube also be angled a bit? Like it doesn't look perpendicular to me.
No,
Yeah.
I think the tube is straight. I think the patient just has the shoulder scrunched up like this.
They probably just did like this or something.
They probably did like this.
Yeah.
Right, so, right, remember when you roll the shoulders, make sure you don't scrunch the shoulders up, or else the clavicles look like this, right? Super high angle.
Because when you hold the back
scapula,
thing, sir, she made me hold it down. She said, if you hold it on the top, this gets up.
Very good, that's correct. Right, and by the way, right, notice, if I try and go back here, save changes to study, yes or no?
No.
No, goodness, right? All right, very good.
From my experience.
So, edge enhancement. Now, I don't know if you noticed when I was doing edge enhancement, but the image also seemed to get a little bit noisier. It seemed to get a little bit more static as I enhanced it further and further. Right? So with edge enhancement, it does also increase noise. Right? So the image looks noisier, even though the edges look sharper. All right, fun one. Equalization.
Denzel Washington.
So this is also similar. This is a similar idea to rescaling. Right? Basically, we share an image. It has only a narrow range of colors, right? So it looks kind of gray. It looks kind of washed out. So equalization just increases the range of the grayscale, and so our contrast now looks better. Almost like how we did it with automatic rescale.
So if it doesn't work out, we need to do this.
So if your automatic rescaling doesn't work out, you can always try to equalize your image.
Really?
How do you, what if,
Your console may or may not have options to do so. Next up, smoothing. This is a form of digital noise suppression. So, remember, how do we get a noisy image? Right, not enough mass, underexposure, right? This is motto, right? Your quantum motto, your quantum noise. So, properly exposed image, noisy image. So if you use too low of a technique, it is possible to try and make it look better by smoothing the image. So you post-process, you smooth it out, and it takes this noisy image, and it makes it look nicer. It makes it look more like the original.
So you take the noise out, basically.
Correct. It's the way to try and remove the noise from the image.
Sir, can I ask a question?
Yes.
The original is so good, why did you make it noisy and then smooth?
So this is a shot with correct KVP and mass. This is an X-ray with incorrect KVP and mass. Instead of shooting the patient a second time to get the correct KVP and mass, you could just try to smooth the image. It's not going to look as good, but it looks better, and you don't reshoot the patient. Yes, Jay?
How would an image with poor technique look if you both adjusted the sharpness and then smoothed it out? Because it does get a bit like noisy whenever you get it like super sharp.
That's a great question. I do not know how they interact. I do not know how those two interact. Digital annotation.
Yes.
My favorite.
Yeah.
Favorite. So, what is rule number 1 about digital annotation?
Do it.
Use them all the time.
Only for tests.
What is rule number 1? Everyone, all together now.
Always cover anatomy of interest.
Should not be used in place of what?
Side markers.
Okay. Need to hear more than just Charles and Shaheen?
Should not be used in place of
Annotation should not be used in replacement of
There you
the
go.
anatomical sector.
There you go.
Okay, what on earth is an anatomic side marker?
That's a good one.
Yeah, that's right. Hold them up. Show me your anatomic side markers.
Wherever everyone
Put your markers in the sky.
Alright, very good. Right?
Got that J. Cole?
So, digital annotation. You should not use this in place of
Yeah, he
physical
could.
markers.
He sensed it.
Should not, right? All images should have a physical marker. So, what's the purpose of digital annotation?
He felt a disturbance in the force.
Ask the people who made that
So,
because
what-
they shouldn't have.
Right, so what's the purpose of digital annotation if you can't use it to mark your images?
No.
You
In-
can use
Legal
marker
document.
images.
No, you can't, right? You can't. Image is a legal document. You cannot use it to mark your
You
images.
failed.
Yes.
Well,
If I should not.
in the event
Should
that
not.
you clicked your marker or something happened to it, I assume that they would just throw it up there to say like, hey, it happened.
Okay, so you can use it as a safety
A
backup.
buffer.
So like, let's say that you do a lateral chest, your marker got burnt out, it's on the image, if you adjust the contrast or brightness, you can see it, but you just want to make it clear it's that side, so you just throw on a digital left marker.
For patient's sake.
As an addition. Okay, I can see an argument for that.
Or
I
you
can
have
see
to
an
make a
argument for
statement,
that.
you replace it.
Right, but what else can you use it for, right? So-
Notating the
Position,
Right.
location.
Annotations.
The babies.
So, patient position, right? You can use it to annotate like supine, upright, weight bearing, semi-erect, decubitus, right? Left decube, right decube, flexion, extension. For example, if you do a small bowel follow through, right? How long? Wait,
Yeah.
did you know what a small bowel follow through is?
Isn't that just like number
Going to
two?
the restroom?
Yeah,
Okay.
that's number two. You
Oh.
following through.
Oh my, you guys are in for
Taco
a
Bell.
treat. You guys are in for a treat.
Oh.
All right, small bowel follow through.
You're getting happy. Okay.
Well, did you need something? Or- No? Okay.
I sensed you were talking about digital markers.
Ah,
Seems like my ears
just in time.
It's so nice to use.
All right, so small bowel follow through. Think of an upper GI exam,
Yes.
right? And after the upper GI exam, there's barium in the GI tract, right?
That's correct.
And the barium makes its way through and then it comes out the other end, right?
Yes.
But some people are constipated. It takes a while for it to go through, right?
That's correct.
Some people may have an obstruction, right? Maybe it's intersusception, maybe it's volvulus, right? Something like that to keep it from traveling through.
Okay.
So, what do? We do a small bowel follow through. After they ingest the barium, we take pictures and watch it as it travels through the GI system and watch its progress all the way through into the large bowel, right? So from stomach to large bowel, we watch it travel through that small bowel. And so you have to take pictures like every 10 minutes or every 15 minutes as it travels through, right, to demonstrate what it's doing. Sometimes it goes through nice and easy. You're done in 30 minutes. Sometimes that patient is there for 2.5 hours and you're like, when is this contrast gonna finally hit the cecum, right? Or, not cecum. When is it finally even gonna hit the ileum, right? When is this contrast gonna reach the ileum? It's stuck in the jejunum for like 2 hours. Right? So, small bowel follow through. You need to mark when you shot the image, right? This is like 15-minute shot, 30-minute shot, 45-minute shot, 1 hour, 1 hour 15, right? So, marking your time. Okay. Does that make sense?
Yeah.
Right. Yeah. Really fun exam.
I'm gonna ask.
Hopefully you all get a chance to see that small ball follow through.
Can we get a Codex in here, please?
All right, just real quick, some final ones. Image flip. I'm sure you've all seen your text do this, right?
Yeah.
Just gotta flip it PA to AB or vice versa, right? Make sure it's the correct direction for the radiologist to read it. Right, you do it CR, you have the green strip pointing the wrong way, your foot comes up, upside down. Right, just flip it around. Make sure it's pointing the correct way. Image inversion. Just flip colors. Right, black becomes white, white becomes black. Nice and easy. And then magnification. Make things bigger. And that's it. That's your post-processing.
So why would you make black into white and white into